Good morning. I am Prasannanjaneya Reddy, working as Assistant Professor in the Department of ECE, Institute of Aeronautical Engineering College, Hyderabad. In this session, we are going to discuss about task scheduling. So, for this topic, we are following the textbook is Introduction to Embedded System by Shibu KV, second edition. So, if you look at this example, here we are following preemptive priority scheduling algorithm. In this preemptive scheduling algorithm, we are taking two processes P1, P2. Process P1, process P2. Here process P1 executes, as I mentioned, 7.5 units of execution time. Process P2, 10 units of execution time. And it sleeps, this is units of execution time. And sleep time is P2 sleep 5 units of execution time, sleep time. P1 sleeps 17.5 units of execution time. So P1 is lowest priority, P2 is highest priority. Okay. If you look at this example, we are taking two processes, P1 and P2. P1 executes, execution time is 7.5 units of execution time and sleeps 17.5 units of execution time. Whereas P2 executes 10 units of execution time and sleeps 5 units of execution time. And here P1 is lowest priority and P2 is highest priority. So if you look at this preemptive priority execution time, we already said ready state, running state, completed state, and wait state, and it goes to the ready state. So initially at the time of 0, process P1 and P2 are available in the ready state. The scheduler checks the ready state, what are the process available, and based on the scheduling algorithm, here we are following preemptive priority scheduling algorithm. Okay. So among P1 and P2, P2 is the highest priority. That's why P2 is scheduled for execution. So P2 is going to the running state. And so P2 goes to the running state. R means running. Here check here. R means running. And P1 is in the ready state. After 10 milliseconds of execution time, P1 goes to the ready state, means that is goes to the waiting state. After 5 milliseconds, it is entered into the ready state again. Okay. At the time of 10th millisecond, again the scheduler checks the ready state. What are the process available? So the available process is P1. So that is scheduled for execution. So P1 is scheduled for execution. So P1 is in the running state. At the time of the 15th millisecond, since P2 is entering from waiting state to ready state and it is preemptive, means if any new process enter into the ready state, the currently executing process is temporarily suspended, and compare the currently executing process with the new coming process based on the scheduling algorithm. Here, scheduling algorithm is preemptive priority. So, P2 priority is comparing with the P1 priority. So, among P1 and P2, P2 is the highest priority. So, again P2 goes to the running state and P1 goes to the ready state. So, P1 is preempted. Yeah, at this time, the program counter value, the stack memory values, all these are saved. That is called context switch. Okay. Again, after P2 execution time is 10 units of time. So, 15 plus 10, 25 milliseconds. At the time of 25th millisecond, again P2 goes to the waiting state. P2 goes to the waiting state. At that time, again the scheduler check the ready state. What are the processes available here? Again, at the time in the ready state only P1 is available. So P1 is scheduled for execution. So P1 is entering into the running state. P1 is already executing 5 units of execution time. Remaining execution time is 2.5 units. So 27.5. At this time, that execution is completed and it is goes to the again waiting state. So its execution is completed. This process is repeated infinite time. That's why the P1 is goes to the waiting state. In general, whenever any process execution is completed, that is enter into the completed state. But here in this requirement, the process P1 and P2 are executed repeatedly. So after completion of its execution, process P1 goes to the waiting state. And again, at the time of 30th millisecond, after 5 milliseconds means 25th to 30 milliseconds, P2 is in the waiting state. After 5 milliseconds means at the time of 30th millisecond, P2 is entered into the ready state. And again, at the time of 30th millisecond, that is scheduled for execution. So, P2 is entered into the running state. P2 enter into the running state. Again, after 10 units of time means 30 plus 10. 40 units of time. Okay. At the time of 40 units of time, P2 is going to the waiting state. P2 going to the waiting state. How much time? 5 units of time. So up to 45 units of time, it goes to the waiting state. Again, P1 also is in the waiting state. How much time P1 waiting time? P1 sleeps 17.5 minutes of time. Here already it is waiting 27.5 to 45. Means how much? 2.5 plus. So 17.5 units of execution. After 17.5 units of execution time, P1 enter into the ready state. Okay. Again, at that time, at the time of 45 milliseconds, 45 units of time, among P1 and P2, P2 is highest priority. So P2 is scheduled for execution. Okay. That's why it's showing it is enter into the running state. It is in the running state. And P1 is in the ready state. Okay. After 10 minutes of time, P2 again enter into the waiting state. At that time, again the scheduler checks at the time of 55 units of execution time. So what are the processes available in the ready state? At that time, P1 is only available. So P1 is entered into the running state. At the time of 60th millisecond, means after 5 minutes of time, P2 is entering from waiting state to the running state again. ready state. Since P2 is highest priority, P2 is scheduled for execution. So P2 is preempt the means currently executing task P1 is temporarily suspended. That is enter into the ready state again. And P2 is enter into the running state. Okay. So P2 executes 10 units of time. So after 10 units of time means 70. At the time of 70th units of time, P2 is enter into the waiting state. Okay. At that time, what are the, again the scheduler checks the ready state always. So what are the processes available in the ready state? At that time, P1 only available in the ready state. So that is scheduled for execution. That is enter into the running state. After 5 milliseconds, okay, after 7, so already it is 5 minutes after executed, remaining execution time is 2.5 units. So total 7.5 units of execution time. After that, P1 is enter into the waiting state. Okay. In this time, the process is in ideal mode. No processes are available at this time. 72.5 units of time. P1 is in the waiting state. P2 is in the waiting state. So no processes available in the ready state. In this time, the scheduler executes the ideal mode operation. Means the CPU is in ideal mode. The CPU is in ideal mode. Again, after 2.5 means after 5 milliseconds, in the sense 75 units of execution time. Again, the process P2 enter into the ready state from running state. So at that time, again, P2 is scheduled for execution like this. This process is repeated infinite times. Like that, the scheduler schedule the process based on the scheduling algorithm. Okay. Example. In our desktop computer or laptop computer, if you press Ctrl Alt Delete, then we will get Task Manager. If you look at this task, if you select this Task Manager, we will get this processes, performance, app history, startup, users, corresponding details and services. First, we will check the process. What are the processes running in our laptop or desktop? If you look at this example, here Microsoft Edge is running, PowerPoint is running, Paint is running, Task Manager is running, and Windows Explorer is running. 5 apps are running front side. In the background process, remaining different types of processes are running background in the background mode. So each process has particular ID. Suppose if you look at the PowerPoint, that process ID is 19916. Its process name is PowerPoint.exe. And it occupies 0% CPU. It utilizes the CPU is 0%. It occupies 85 MB memory. And memory in the sense RAM. Here that is RAM. This is ROM. Okay. Like this. Next we will check one more example. If you look at this anti-malware service executing. So if you look at the remaining process, suppose Microsoft had utilized the CPU 0.3%. Task Manager utilized the CPU is 0.6%. And Windows Explorer utilized the CPU is 0.1%. Its process ID is 23472. Its process name is Explorer.exe and utilized the 0.1% CPU it occupies 41.9 MB RAM, and it occupies hard disk is very less and very low. Power usage is very low, and GPU 0 per low, and network is very low, 0. Okay. Here we are following Windows 10 operating system. In that it contains kernel. This kernel follows different scheduling algorithms. So based on that, it will assign process IDs. This is process name. How much percentage of the CPU is being utilized? How much RAM memory is utilizing here? How much hard disk is utilizing here? How much internet is utilizing here? And how much power is consuming here? So check the various process. So like this, the Windows 10 operating system kernel schedule these processes and assign process IDs and do the operations. Next, queues. Queue means first in first out structure, like we are taking train tickets in the railway queue or anytime. So the process which wants to write the data into one side, and the process which requires the data, which reads the data from another end. So the process which create the write the data, that is server, and which reads the data, that is client server architecture. Next, semaphores. Semaphore means like a key. Suppose we having some digital dashboard or notice board. Different people wants to display different types of information, but the space is limited. At that time, which one is highest priority or which one is having key, that person only display his content in the notice board. Okay, semaphore is like a key. The process which is having the key, that utilizes the corresponding resource, either dashboard, either memory, either CPU, whatever may be. So semaphores are a tool used in computer science to help manage how different processes or programs share resources like memory or data without causing conflicts. A semaphore is a special kind of synchronization data that can be used only through specific synchronization primitives. Semaphores are used to implement critical sections, which are regions of code that must be executed by only one process at a time, like traffic signal also. At a time, in one direction only, the vehicles will be allowed to travel. If all persons coming in all directions, means that traffic will be stopped. Means it is somewhat difficult to allow which vehicle will be transmit. Similar in the same manner here also. If more than one process wants the same resource, means which process wants to access the resource, that is decided by the key. So by using semaphores, processes can coordinate access to shared resources such as shared memory and IO devices. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.